Today we are going to discuss about problems related to pressure measurements. Right, please note down the problem. A hydraulic press has a ram of 30 centimeters diameter . 30 centimeters diameter and a plunger of 4.5 centimeters diameter . Find the weight lifted by the hydraulic press when the force applied at the plunger is 500 newtons. 500 newtons. Right, this is the given problem. In this problem, they have given diameter of the ram is 30 centimeters and diameter of the plunger is 4.5 centimeters. Force applied at the plunger is 500 newtons. Find the weight lifted by at the ram. So first we are going to draw the diagram. This is ram, this is plunger, right? The diameter of the ram is given, that is equal to, diameter of the ram is equal to 30 centimeters, right? Diameter of the plunger is equal to 4.5 centimeters. Now here apply Pascals law. Pascals law states that the intensity of pressure at a point equal in all directions. If the fluid is at static condition, the pressure at a point is equal in all directions. That means the pressure at the plunger must be equal to the pressure over the ram. This is the Pascal's law. Now we are going to determine the pressure at plunger. Pressure at plunger, intensity of pressure P is equal to, intensity of pressure P is equal to force by area. Intensity of pressure P is equal to force by area. That is the formula already I have given in the last class. Force given, that is equal to 500 newtons divided by area. Say area of the plunger is taken as small a. Small a is equal to pi d square by 4 pi into diameter 4.5 centimeters, that is equal to 0.045 meters, 0.45 square divided by 4. Therefore area of the plunger is equal to 0.0150 meter square, right? Now and again area of the ram, that is also same formula, pi d square, capital D square by 4. This is equal to pi into d is nothing but 30 centimeters, that is equal to 0.3 meters divided by 4. Therefore dia of the ram is equal to 0.3 meters. Therefore area of the ram is equal to 0.070 meter square. Now we are going to determine the pressure intensity at the plunger. Pressure intensity is equal to force by area. Force equal to 500 newtons, that is given in the problem. Right, area is equal to, already we have determined here, that area is equal to 0.0015. Therefore this is the pressure intensity, right? This is the pressure intensity at the right. Pressure intensity at the plunger is equal to 500 divided by 0.015 area. Now same pressure intensity is applied at the ram. Therefore pressure intensity at ram At RAM, pressure intensity is equal to same value, that is equal to 500 divided by 0.0015 based on Pascal's law. Pascal's law states that at a point the pressure intensity is equal in all directions if the fluid is at static. Based on that statement, the pressure intensity at RAM is equal 500 divided by 0.0015, same pressure intensity where the pressure intensity at the plunger, right? But as per given problem, we are going to determine the what is the weight lifted at the RAM. Weight lifted at the RAM, that means the pressure intensity at the RAM is equal to, as per given, pressure intensity at RAM is equal to force or weight lifted by area. Weight lifted denoted by capital W. Area, that is area already we have determined, weight lifted W divided by area, that is equal to 0.070, right? This is the, as per the RAM, the pressure at RAM is equal to weight by area. Weight we are going to determine, area is already calculated here, but this is equal to, already based on the Pascal's law, the pressure intensity at the plunger is equal to pressure intensity at the RAM, that is equal, this is the value. Therefore, this value is equal to W by 0.07. Therefore, this is equal to 500 divided by 0.015. Therefore, finally unknown is W. Weight lifted at the RAM, W is equal to, weight lifted at the RAM, W is equal to 2222 newtons or 22.22 kilo. This is the weight lifted at the RAM. Please note down another problem. A hydraulic press has a ram of 20 centimeters dia. Dia is equal to 20 centimeters. Capital D is equal to 20 centimeters. And the plunger of 3 centimeters dia, plunger is equal to 3 centimeters, small d is equal to 3 centimeters. It is used for lifting a weight of 30 kilonewtons. Weight equal to 30 kilonewtons. Weight given, that is equal to 30 kilonewtons. Find the force required at the plunger. What is the force required at the plunger? This is the reverse direction. This is also as like as earlier problem, but earlier problem they have given force applied at the plunger, we have determined the weight lifted at the ram. But in this problem, weight lifted at the ram given, that is 30 kilonewtons. What is the force applied to lift this 30 kilonewtons weight? How much force is applied at the plunger? That we are going to determine here, right? Based on the Pascal's law, the pressure intensity at the plunger must be equal to the pressure intensity at the ram, or the pressure intensity is equal in all directions at a point if the fluid is at static condition. Therefore, pressure intensity at the plunger equal to force by area. Force by area. Area means area of the plunger, that is equal to force, that is unknown, divided by area pi d square. Diameter of the plunger is equal to 3 centimeters, that is equal to 0.03 meters, pi d square by 4. This is the pressure intensity at the plunger. Based on the Pascal's law, pressure intensity at the ram is equal to same pressure intensity, that is equal to F divided by pi 0.032 3 square divided by 4 based on the Pascal's law, right? Now the weight lifted at the ram is given, that is 30 kilonewtons. Now as per the given data, pressure at ram is equal to weight by area. What is the weight? Weight is given here, that is denoted by W, divided by area. Area of the ram, that is equal to, what is the weight? That is 30 kilonewtons. 30 into 1000 newtons divided by area, that is equal to pi. What is the diameter? diameter of the ram is given, that is 20 centimeters, that is equal to 0.2 meters square divided by 4. Right, as per the Pascal's law, this is equation number 1, this is equation number 2, equation number 1 is equal to equation number 2. Therefore, F divided by pi 0.03 square divided by 4 is equal to weight 30 into 1000 divided by pi 0.2 square divided by 4. In this equation, only unknown is F, all are known parameters. Therefore, force required at the plunger to lift the 30 kilonewtons force at the ram is 675.2 newtons. This is the force required at the plunger to lift the 30 kilonewtons weight at the ram. Right? Note down one more problem related to the pressure and its measurements. Calculate the pressure due to column of 0.3. Calculate the pressure due to column, that means head 0.3 of water. So this is the pressure head given, that is H is equal to 0.3 meters. What is the pressure for water? And then what is the pressure for oil of specific gravity? Oil of specific gravity 0.8. What is pressure? And third one, mercury of specific gravity 13.6. Mercury of specific gravity 13.6. What is the pressure? Density of water is taken as rho is equal to 1000 kg per meter cube. Density of water is taken as 1000 kg per meter cube. This is the given problem. They have given the column of liquid, that is equal to 3 meters. What is the pressure intensity because of 3 meters water column? If that is the water, what is the pressure intensity if this is the oil head is equal to 0.3 meters, what is the pressure intensity? Specific gravity of oil is given, that is 0.8. And if suppose this water column is H, mercury head is equal to 0.3 meters, what is the pressure intensity if the mercury specific gravity is given, that is 13.6. First we are going to determine the pressure with respect to water. Standard formula, pressure equal to WH. W is the unit weight of liquid, H is the head or water column. Or this is also, W is also nothing but rho G into H. Rho is the density of the liquid, G is the acceleration due to gravity, and into H is the liquid column. Right here, first we are going to determine the pressure intensity for the water. Water density, standard liquid density or water density is equal to 1000 kg per meter cube. 1000 into G value 9.81 into H is given 0.3 meters. Therefore, the pressure due to water column 0.3 meters is, therefore the pressure intensity because of the 0.3 meters of water column is equal to 2943 Newton per meter square. This is the pressure intensity because of the water column 0.3 meters. And the next problem, if the liquid column is 3 meters, that is the oil of specific gravity 0.8, what is the pressure intensity? Same formula, pressure intensity P is equal to WH. W is also nothing but rho G H. Here rho is nothing but density of oil. Rho is nothing but density of oil here. If density of any liquid is equal to specific gravity of that liquid into density of the standard liquid, that I have given in the last class. Density of any liquid, for example density of oil is equal to specific gravity of oil into density of standard liquid. Right here, specific gravity of oil given, that is equal to 0.8 into density of standard liquid or density of water, that is equal to 1000 kg per meter cube. Right, this is the density of oil. Therefore, this is equal to rho is nothing but density of oil into G into H. This is equal to density of oil, that is equal to 0.8 into 1000 into G value 9.81 into H, that is equal to 0.3 meters. Therefore, the pressure intensity P equal to, because of oil, pressure intensity P because of oil column 0.3 meters equal to 2354 Newton per meter square. Right, this is the pressure intensity. And last one, if 0.3 meters of mercury had, what is the pressure intensity? The mercury specific gravity is given here, that is equal to 13.6. Here also same formula, pressure intensity P is equal to WH, that is equal to rho G H, that is equal to rho means rho of Hg, density of mercury into G into H. Right, first we are going to determine the density of mercury is equal to specific gravity of mercury into density of standard liquid, that is equal to 1000. Therefore, pressure, because of the mercury had 0.3 meters, pressure is equal to rho Hg into G into H, that is equal to rho mercury density is equal to 13.6 into 1000 into G value 9.81 into depth of mercury, that is equal to 0.3. Therefore, pressure because of the mercury column 0.3 meters is equal to 40025 Newton per meter square. What we have observed here, because of the water, the pressure equal to 2943 Newton per meter square. Because of oil, 2354 Newton per meter square. Because of mercury, column head 0.3 meters, 4.0025 Newton per meter square. Based on this problem, we observed that the pressure intensity is more in case of mercury if the 0.3 meters of depth of mercury gives the pressure intensity is equal to 40025 Newton per meter square. The same depth 0.3 meters of oil, the pressure given, that is equal to 2354 Newton per meter square. Same depth 0.3 meters of water column, the pressure intensity is equal to 2943 Newton per meter square. Right, now we are going to solve one more problem related to pressure calculations. Please note down, the pressure intensity at a point in a fluid is given 3.924 Newton per cm square. Find the corresponding height of fluid when the fluid is water, and another one when the fluid is oil of specific gravity 0.9. Oil specific gravity 0.9. Right, here in this problem they have given the pressure at a point that is equal to 3.924 Newton per cm square. Find the what is the head. We know one standard formula. First, pressure P is equal to pressure intensity or intensity of pressure or pressure P is equal to WH. This is also nothing but rho GH. From this equation, head liquid height is equal to intensity of pressure divided by rho G. But here the pressure is given, that pressure is equal to 3.924 Newton per cm square, that is equal to 3.924 into 10 power 4 Newton per meter square. Right, pressure we know that is equal to 3.924 into 10 power 4 Newton per meter square, that is equal to 3.924 into 10 power 4 divided by, now first we are going to determine the liquid column, first we are going to determine the water column, that is equal to head of water is equal to pressure intensity divided by rho. Density of water is equal to 1000 kg per meter cube. This is rho is nothing but density of water. Here we are going to we have taken here liquid, that is the water. Therefore density of water is equal to 1000 kg per meter cube into G is equal to 9.81. Therefore the head of water required because of this pressure is equal to 4 meters of water, 4 meters of water. And another problem, they asked that question number 1, what is the water column required because of this pressure? What is the oil column required? That specific gravity of oil is 0.9 because of the pressure is equal to 3.924 into 10 power 4 Newton per meter square. Therefore oil column is equal to pressure divided by density of oil into G. This is equal to pressure, that is equal to 3.924 into 10 power 4 divided by density of oil. Density of any liquid is equal to specific gravity of that liquid into density of the standard liquid. That formula already I have given. Therefore density of oil is equal to specific gravity of oil 0.8 into density of the standard liquid, that is equal to 1000 kg per meter cube into G 9.81. Therefore from this equation the oil column required, the oil column is equal to 4.4 meters of oil because of this pressure. Because of this pressure the oil column is equal to 4.4 meters of oil, right? And please note down one more problem. An open tank contains water up to a depth of 2 meters and above it an oil of specific gravity for a depth of 1 meter. This is oil of specific gravity 0.9. This is water. The depth of oil is 1 meter. Find the pressure intensity at the interface of the two liquids. What is the pressure intensity here? And second one, at the bottom of the tank, what is the pressure intensity here? Right, based on this problem we are going to determine the pressure intensity at the interface of the liquid, that means interface of the water and oil, P. And also one more problem, what is the pressure intensity at the bottom of the tank? First we are going to determine the pressure intensity at the interface of the water and oil. We know one standard formula, pressure intensity P is equal to WH, right? W is nothing but rho G into H. So now we are going to determine the pressure intensity at this point. Therefore above this point the liquid is oil, so that this is equal to density of oil into G into H. Density of oil first we are going to determine. Already I have explained to you, density of any liquid is equal to specific gravity of that liquid into density of the standard liquid, right? Density of the oil is equal to specific gravity of the oil, that is given 0.9 into density of the standard liquid, that is 1000 kg per meter cube. Standard liquid is nothing but water, and head given, that is equal to 1 meter. Therefore the pressure intensity at the interface of the water and oil is equal to 8.24 Newton per meter square. The pressure intensity interface of the oil and water is equal to 8.24 Newton per meter square. Now we are going to determine the pressure intensity at the bottom of the tank. Here also same standard formula, pressure intensity is equal to WH. This is also written as rho GH. Here we are going to determine the pressure intensity at the bottom. That means two liquids. One is rho oil into G into H1 plus density of water into G into H2. Say this is equal to H2, this is equal to H1. Now, therefore, pressure intensity at the bottom of the tank is equal to density of the oil, that is equal to 0.9 into 1000 into G value 9.81 into H 1 meter plus density of water, that is equal to 1000 kg per meter cube, because the liquid is water here, into G 9.81 into depth of water column, that is equal to 2 meters. Therefore, the total pressure acting at the bottom of the tank is equal to 28449 Newton per meter square. Right? These are the problems related to pressure measurements. Right? Now we are going to solve some problems related to the monometers. Before going to solve the problems related to monometers, first you are going to draw the diagram. Based on the given problem, first we are going to draw the diagram, then only solve the problem. Right? Please note down the problem. The right limb of simple U-tube manometer containing mercury is open to the atmospheric. Right. Here, U-tube manometer, the one of its end is open to the atmospheric. Say this is the datum line, already I have given derivation. Right. This is the liquid flowing through the pipe. The one of the end of the U-tube manometer is connected to the pipe and another end is open to the atmospheric. Here in this problem, the right limb of the single U-tube manometer containing mercury, say this is equal to specific gravity of the mercury is Sm, density of the mercury is rho m. Right? While the left limb is connected to a pipe in which the fluid of specific gravity 0.9. The specific gravity, say this is S1, specific gravity of the fluid flowing in the pipeline is given, that is equal to 0.9. The center of the pipe is 12 centimeters below the center of the mercury. The center of the pipe, this is the center line of the pipe. The center of the pipe is 12 centimeters below the level of mercury in the right limb. Say this is the level of mercury in the right limb. The center line of the pipe is 12 centimeters from the level of mercury. That means this is the mercury. So if the pipe is connected to the pipe, the pressure is more in the pipe. Because of the pressure, the mercury is moving towards right side. This is the water or liquid. The specific gravity up to this point, up to datum line AA is 0.9. Left side above the datum line AA, specific gravity is equal to, that is equal to 13.6, because 13.6, this is the mercury. Right? Find the pressure of fluid in the pipe if the difference of mercury level in the two limbs is 20 centimeters. Difference of mercury level between two limbs is given, that is equal to 20. This is the mercury level in the left limb, this is the mercury level in the right limb. The difference between two limbs is 20 centimeters. Here, find the pressure of fluid in the pipe. What is the pressure of fluid? That is equal to PA. This is point A. In this case, we are going to determine the above the datum line left side pressures and also determine the above the datum line right side pressures. The left side pressures must be equal to right side pressures above the datum line. Then we are going to determine the what is the pressure at the point A. Right? Now, left side pressures. What are the left side pressures? One left side pressure, because of the liquid column, this is the liquid column. Here, up to this point, this is the liquid flowing in the pipe, that is equal to, what is the depth? Total depth is equal to 20 centimeters. This is the 12 centimeters. Automatically the depth of liquid is equal to this is equal to, or H1 is equal to 8 centimeters. Depth of liquid in the left limb is equal to 8 centimeters. Okay. Now one pressure we are going to determine, that is the pressure at point A, and another one is the, because of the liquid column, H1, that is equal to 8 centimeters in the left side. Right side pressures, only one liquid column, that is the mercury column, that is equal to 20 centimeters. Because of the 20 centimeters mercury column, we have one pressure. Therefore here left side pressures must be equal to right side pressures. Right, what are the left side pressures? Left side pressure PA, left side pressures. One is PA, pressure intensity at point A, plus, because of this water column, we have one pressure, that is equal to, pressure is equal to, what is the formula? Rho 1 G H1. Right, the liquid column rho is given, that is equal to, rho is not given, that we are going to determine. S is given, S1 is given, that is equal to 0.9. H1 is equal to 8 centimeters, that is equal to 8 centimeters. H1 is equal to 8 centimeters, that is equal to 0.08 meters. Therefore PA plus rho 1, that means density of the flowing liquid is equal to specific gravity of the flowing liquid into density of the standard liquid, that is equal to, density of the flowing liquid is equal to specific gravity of the flowing liquid 0.9 into density of the standard liquid 1000. Right, and G 9.81 into, what is the H1? The liquid column is equal to 0.08 meters. This is the left side pressures. And right side pressures, only one column in the right side above the datum line AA, that is equal to rho G H, rho 2 G H2, that is equal to, rho 2 is nothing but density of the mercury, that means specific gravity of the mercury into density of the standard liquid, into G value 9.81 into H2, that is equal to 20 centimeters, so that is equal to 0.2 meters. These are the right side pressures, these are the left side pressures. Equating these two for equilibrium condition, therefore PA plus 0.9 into 1000 into 9.81 into 0.08 is equal to 13.6 into 1000 into 9.81 into 0.2. Here only unknown is PA. Therefore the pressure at point A, PA is equal to 25977 Newton per meter square. The pressure at point A equal to 25977 Newton per meter square. Right? This is the one problem related to manometers. Please note down another problem. Already I told you before going to solve the problems related to YouTube manometer, differential manometers, or a single column manometer, any manometers, first we are going to draw the diagram based on the given data, then only solve the problems. Right? Please note down. A simple YouTube manometer containing mercury is connected to pipe in which a fluid of specific gravity is 0.8 and having vacuum pressure is flowing. Vacuum pressure. Based on the vacuum pressure, we are going to draw the diagram. This is the left limb open to atmosphere. This is the datum line AA. Here what is happening? The pressure in the pipeline is vacuum, that indicates that the mercury moves towards left. This is the, suppose this is the mercury level. This is the mercury moves towards left because of the pressure in the pipe is negative. A simple U-tube manometer containing mercury is connected to a pipe in which a fluid of specific gravity 0.8, specific gravity given 0.8, and having vacuum pressure is flowing in this pipe. The other end of the manometer is open to the atmospheric. Find the vacuum pressure in the pipe. What is the vacuum pressure at point A or in the pipe? If the difference of mercury level in the two limbs is 40 centimeters, difference of mercury level in the two limbs is 40 centimeters. This is the datum line AA. This is the mercury level in the right limb. This is the mercury level in the left limb. The difference of mercury level between the two limbs is 40 centimeters because we have taken 40 centimeters in the left side because the pressure in the pipeline is negative pressure, right? And the height of fluid in the left limb from the center of the pipe is 15 centimeters. The liquid in the left limb is 15 centimeters. This is the given problem. Based on this problem, we are going to determine the pressure at point A or the pressure or the vacuum pressure in the pipeline A. Right here also, we are going to determine the pressures in the left side of the section AA or datum line AA, right side pressures above the datum AA. Now equating these two, finally we have the pressure at point A. Right? First, left side pressures. What are the left side pressures? Because of the pressure in the pipe A, that is equal to PA. Pressure in the pipe A is denoted by left side pressures is equal to pressure at point A plus, because of this column we are having one pressure. Because of this column also we are having one more pressure. Say this is equal to H1. Say this is equal to H2. Right? Now pressure is equal to rho 1 G H1 because of this column, and because of this column rho 2 G H2. These are the left side pressures. This is equal to P A plus rho 1. That means density of the flowing liquid, specific gravity of the flowing liquid given 0.8. Density of the any liquid is equal to specific gravity of that liquid into density of the standard liquid. Therefore, rho 1 is equal to specific gravity of that liquid, that is equal to 0.8 into 1000 is the density of the standard liquid into 9.81 G value H. H is equal to 15 centimeters. So H1 is equal to 15 centimeters. That is equal to 0.15 meters. Into 0.15 meters plus rho 2. Rho 2 is nothing but this is the depth of column. Corresponding depth, the liquid is mercury. Mercury density is equal to specific gravity of the mercury, that is equal to 13.6 into 1000 into G 9.81 into H. The mercury level is 40 centimeters, that is equal to 0.4 meters. Right? This is equal to 0.4 meters. These are the left side pressures. Then right side pressures. Right side pressures is equal to, above the datum line AA, there is no liquid in the column. Right side column, right side limb, right side glass tube, there is no any liquid in the right side limb. Therefore the pressures, there is no H, there is no pressure. P is equal to WH, H is equal to 0. P is equal to WH, H is equal to 0. Automatically pressure is equal to 0. Therefore the pressures in the right side is equal to 0. Now this is equation number 1. This is equation number 2. Now equating the left side pressures must be equal to the right side pressures. Therefore left side pressures PA plus 0.8 into 1000 into 9.81 into 0.15 plus 13.6 into 1000 into 9.81 into 0.4 is equal to 0. Left side pressures must be equal to right side pressures. Only unknown is PA. All are known to us. Therefore, pressure at point A, that we should have negative value, because the pressure in the pipe is a vacuum that is given in the problem. Therefore, the pressure at pipe A, PA, is equal to 54543. 54543 Newton per meter square. This is the pressure in the pipe A, that is the vacuum pressure, minus 54543 Newton per meter square. Right? A single column manometer is connected to a pipe containing a liquid of specific gravity 0.9 as shown in figure. Right? Single column manometer. This is also as like as YouTube manometer, but only the difference is here we are going to take one reservoir, that the reservoir area is approximately 100 times the diameter of the pipe in the left limb or pipe in the right limb. A single column manometer is connected to a pipe containing a liquid of specific gravity 0.9 as shown in figure. Right? This is the mercury or manometer liquid. This is the liquid in the pipe. Because of the pressure, this is moving like this. Because of the pressure, the mercury level moves towards the right side. This is the right limb. This is the left limb. Right? Now, the level, this is given, this is equal to 40 centimeters. The mercury level difference that is given up to this one, sorry. Mercury level, this is the mercury level in the left limb, this is the mercury level in the right limb. The mercury level difference between the left limb and right limb is 40 centimeters. And the liquid column, that is center line of the pipe, to the, this is say line AA, that is 20 centimeters. In this problem, find the pressure in the pipe if the area of the reservoir is 100 times the area of the tube for the manometer reading as shown in figure. That means this is the area of the reservoir, this is the area of the pipe. Area of the reservoir equal to 100 times the area of the pipe. This is the condition they have given in the problem. Specific gravity of mercury 13.6 and the specific gravity of the liquid that is given S1 is equal to 0.9. The specific gravity of the mercury, that is say S2, is equal to 13.6. Now find the pressure in pipe A. Say this is point A, the pipe, the pressure in the pipe A, the pressure at point A is PA. Here also equating the left side pressures must be equal to the right side pressures above the datum line AA. But here only in case of a single column manometer, you are going to remember the formula for the determination of the pressure head, or the formula determination of the pressure at point A. Formula pressure at point A, PA is equal to small a, area of the tube divided by area of the reservoir into H2 bracket begin rho 2g minus rho 1g plus rho 2 H2g minus rho 1 H1g. Here all values are known to us. The specific gravity of the flowing liquid is 0.9. The specific gravity of the mercury is 13.6. Now this is equal to the relation between capital A to small a is equal to 100 times. Therefore, small a by capital A, small a by capital A is equal to 1 by 100. This is equal to 1 by 100 into H2. This is H2. Say this is equal to H2. Say this is equal to H1. H2 40 centimeters, that means 0.4 into density of the monometer liquid, that is 13.6 into 9.81 G value. Density of the flowing liquid. Density of the flowing liquid is not given. The specific gravity of the flowing liquid given, that is equal to 0.9. Therefore, density of the flowing liquid is equal to specific gravity of the flowing liquid into density of the standard liquid into 9.81 plus rho, that is equal to density of the monometer liquid. Right here also, specific gravity of the monometer liquid 13.6, density of the monometer liquid 13.6 into 1000 density of the standard liquid. Rho 2 is nothing but density of the monometer liquid, that is equal to specific gravity of the monometer liquid 13.6 into density of the standard liquid, that is 1000 kg per metric cube, into 9.81 G value. Rho 1 0.9 into 1000 density, G value 9.81 plus density of the monometer liquid 13.6 into 1000 into G value 9.81 into H2, that is equal to 0.4 minus rho 1, the density of the flowing liquid 0.9 into 1000 into G 9.81 into H1 is nothing but 0.2 meters, 20 centimeters, that is nothing but 0.2 meters. Right? Here all are known to us. Therefore, pressure at point A is equal to 52134 Newton per meter square. Pressure at point A is equal to 52134 Newton per meter square. Right? Now we are going to solve one more problem. Please note down. This problem is related to differential manometer. A differential manometer is connected at the 2 points A and B of 2 pipes as shown in figure. Right? meters, not 20 centimeters. 2 meters. This is 3 meters. Like this would be extended up to certain level top, because this is 3 meters here. This is 3 meters. This is the liquid flowing in pipe A. This is pipe A. This is pipe B. Right. Here a differential manometer is connected at 2 points A and B of 2 pipes as shown figure. The pipe A contains a liquid of specific gravity 1.5. Specific gravity S1 is equal to 1.5. while pipe B containing a liquid of specific gravity 0.9, specific gravity S2 is equal to 0.9. The pressure at A and B are 1 kg force per cm square. Pressure at A, PA equal to 1 kg force per cm square. Pressure at B equal to 1.80 kg force per cm square respectively. Find the difference in mercury level in the differential manometer. What is the H? This is the differential mercury level difference. Right, this is the problem. This is differential manometer. Here they have connected two pipes. One pipe, one of the U-tube is connected to the one pipe, and another end of the U-tube is connected to the another pipe, that is pipe B, and one end is connected to the pipe A. Right, the specific gravity of the flowing liquid is given 1.5 in the pipe A. The pressure in the pipe A is equal to 1 kg force per cm square. 1 kg force per cm square. Right, and levels also given here. Now we are going to determine what is the H. What is the mercury level difference? This is mercury move towards this side. That means the pressure is more here. Because of that high pressure, the mercury is moving towards left. What is the H? Here also we are going to take the left side pressures and right side pressures. For equilibrium condition, left side pressures must be equal to the right side pressures. Now here pressure at pipe A given, that is equal to PA is equal to 1 kg force per cm square. That first converts into 1 kg force per cm square, that converts into 1 into 10 power 4 kg force per meter square. This is the pressure units in MKA system. Now this converts into SI system. Therefore 1 into 10 power 4 into 9.81, that is Newton per meter square. This is the force, that is the pressure at pipe A, that is 1 into 10 power 4 into 9.81 Newton per meter square. Like that, the pressure in the pipe B also 1.8 into 10 power 4 into 9.81 Newton per meter square. This is the pressure in the pipe A. This is the pressure in the pipe B. This is the pressure in the pipe A. Now left side pressures must be equal to the right side pressures. Finally we have the H. Left side pressures must be equal to right side pressures. What are the left side pressures? One is the pressure at point A, and another one is the pressure because of this column, and another pressure is because of this column, and another pressure is because of this column. Right, in the right side also because of this column, one pressure, that is equal to, this is equal to 2 plus H. The liquid column in the right limb above the datum line A. Right, left side pressures, that is PA. PA is nothing but, right, PA, pressure at point A, plus this is the one pressure, that is equal to rho 1 G H1, plus this is one more pressure. This is also same liquid rho 1 G H2. Say this is equal to H1, this is equal to H2. Right? This is one pressure, this is another pressure, this is one more pressure, plus rho is the density of the heavy liquid is denoted by rho. Specific gravity of the heavy liquid is denoted by S. Right? Rho into G into H. Because of this column had one pressure. Pressure 1 PA in the pipe A, and 3 meters column we have one pressure, and 2 meters column we have one more pressure, and H meters column we have one more pressure. That are the left side pressures. That must be equal to right side pressures. We have only one liquid column here in the right limb above the datum AA, that is equal to 2 plus H, that is equal to rho 2 G. This is nothing but H3. Rho 2 G H3. Right? Now PA, already we know the value of PA, that is equal to 1 into 10 power 4 into 9.81. This is the pressure in pipe A, plus rho 1, specific gravity of the fluid given 1.50. Therefore density is equal to 1.5 into 1000, density of the standard liquid, into G 9.81 into H1. This is H1. H1 is nothing but 3 meters, plus rho 1, same liquid, that is the pipe A liquid, that is equal to 1.5 into 1000 into G 9.81 into H2. H2 is nothing but 2 meters, plus rho, density of the monometer liquid or mercury, that is equal to 13.6 into 1000 into G 9.81 into H. H is unknown, that we are going to determine here. That must be equal to right side pressures, that is equal to rho 2, that means density of the liquid in pipe B, that is given in the problem, 0.9. This is 0.9. Therefore density of the flowing liquid in the pipe B is equal to specific gravity of the flowing liquid into density of the standard liquid. Therefore rho 2 is nothing but 0.9 into density of the standard liquid into 9.81 G value. H3 is nothing but 2 plus H, because this is 2 meters, this is H meters. 2 plus H is the depth of column in the right limb. And also one more plus here, right side pressures, rho 2 G into column plus pressure in the pipe B, that is equal to 1.8 into 9.81 into 10 power 4. Okay, right, all are known to us here, plus 1.8 into 9.81 into 10 power 4. Therefore all heads known to us, only unknown is H. From this equation we are going to determine the unknown parameter H, that is the mercury level difference between the left limb and right limb, that is H is equal to 181 meters. That should be mentioned in centimeters, that is equal to 18.1 centimeters. H is equal to 0.181 meters or 18.1 centimeters. This is the mercury level difference between two limbs. Right? Now we are going to solve one more problem, and last problem. Please note down. Water is flowing through two different pipes to which an inverted differential manometer having an oil of specific gravity 0.8 is connected. The pressure head in the pipe A is 2 meters of water. The pressure in the pipe B for the manometer reading is as shown in figure. Right. So here in this problem they have given diagram. Inverted differential manometer. Inverted differential manometer means the one end of the inverted U tube is connected to the pipe A here, and another end is connected to the pipe B. In this case, inverted differential manometer, we are going to take the manometer liquid is the light liquid. That means the specific gravity of the manometer liquid is less than liquid flowing in the pipe A and liquid flowing in the pipe B. Right? That is denoted by SL. Okay. Right. This is the given diagram. The specific gravity of the manometer liquid is given. That is equal to, specific gravity of the manometer liquid is equal to 0.8. and this is the water. So this is also water. If the water means the specific gravity is equal to 1, automatical density is equal to 1000 kg per meter cube. Right, this is a given problem. Water is flowing through two different pipes, to which an inverted differential manometer having an oil of specific gravity 0.8 is connected. The pressure head in the pipe A is 2 meters of water. The pressure head is given, that is equal to 2 meters of water. Find the pressure at point B. What is the pressure at PB? This is denoted by PB. Right? Based on this problem, we are going to determine the pressure in the pipe B. Pressure in the pipe A they have given. The pressure head is given. Pressure head is given. Therefore, pressure in the pipe A is equal to P is equal to, what is the formula? WH, that is equal to rho GH. But density of the water, that is equal to 1000 into G, 9.81 into H is given, that is equal to 2 meters. This is that is equal to 1000 into 9.81 into 2 Newton per meter square. This is the pressure in the pipe A. Now we are going to determine the pressure in the pipe B. Here also the left side pressures below the datum line. This is say datum line A. Below the datum line must be equal to the right side pressures. Now left side pressures must be equal to right side pressures. What are the left side pressures? One is the pressure because of the pipe liquid, that is equal to PA is equal to, already we have determined, one pressure, and another pressure is because of this water column. This is equal to say H1. These are the left side pressures. And right side pressures, we have two columns. One is the light liquid column, that is equal to 12 centimeters. Say this is equal to HL. Right, and one more column, that 10 centimeters, that is the because of the liquid in the column, liquid in the pipe B, that is one more column, that is equal to H2. This is one pressure, this is the one pressure, two pressures, and one more pressure because of the flowing liquid in the pipe B, that is equal to PB, that we are going to determine. Now left side pressures must be equal to the right side pressures. Left side pressure PA plus, because of this water column, here we are going to take not plus, we are going to take minus. The liquid or manometer liquid is taken as light liquid, that means the specific gravity of the manometer liquid is less than the liquid flowing in the pipe A and pipe B. Therefore, PA minus rho 1 GH1. Rho 1 GH1. The density of the flowing liquid is rho 1, H1 is the depth of liquid. Right? Two pressures, left side pressures only these two, that is equal to right side pressures. One is because of this column, that is equal to rho L, specific gravity of the density of the light liquid, into G into level HL, light liquid level. These are the left side pressures. Right side pressures is equal to below the datum line AA, therefore minus density of the manometer liquid into G into liquid level of the manometer liquid minus, this is the column, that is equal to rho 2 G H2 plus pressure in pipe B, that is equal to PB. Right, now PA already we have calculated here, that is equal to 1000 into 9.81 into 2, this is the pressure in pipe A, minus rho density of the flowing liquid water, that is equal to 1000 kg per meter cube into G, 9.81 into H1, that is level is equal to 30 centimeters, so that is equal to 0.3 meters. 0.3 is equal to minus rho L, density of the manometer liquid is equal to specific gravity of the manometer liquid into density of the standard liquid, that is equal to 0.8 into 1000 density of the manometer liquid into G, 9.81 into HL, the level is equal to 10 centimeters, that is equal to 0.1 meter. that is equal to 0.1 minus rho 2, the density of the flowing liquid here is also water, therefore 1000 kg per meter cube, into G 9.81 into H2. H2 is the level, that is equal to, the level of the light liquid is equal to 12 centimeters, that is equal to 0.12 meters. 0.12 meters here. The level of the liquid in the pipe B is equal to 10 centimeters, that is equal to 0.1. 0.1 here plus PB. Right here, these are the left side pressures. These are the left side pressures. These are the right side pressures. Left side pressures equal to right side pressures. In this equation, only unknown is pressure at point B, in the pipe B, at point B. The pressure at point B equal to 18688 Newton per meter square. The pressure at point B or in the pipeline B equal to PB is equal to 18688 Newton per meter square. These are the problems related to the pressure and its measurement. These are the problems related to the manometers. Thank you one and all.